Week of vector calculus, it'll be due. The person before me didn't charge the microphone, which is lovely. Can you hear me okay if I just yell? Yeah.
How loud you yell.
Depends how enthusiastic I get, that's right. Yeah. Remind me maybe 10, 15 minutes in, and I'll try to put the mic on with the charge by then. Okay, let me just write that explicitly so everyone at home can see this as well. Assignment will be released this week. It will be due. I want to say, let me say it will be, not tentatively. Due on Friday, 2 weeks from now. End of week 5.
What's the likeness policy?
Probably not good. I'm not sure, but it really shouldn't.
I don't plan on being like
There's no reason why it should be. 2 weeks is plenty of time. The amount of content. So at the moment it's 4 questions or something. I'm going to add another one which has week 4 content on it. Maybe another one. It shouldn't take very long. It didn't take me very long. So it didn't take you very long. It has one thing I should mention. You guys can't hear if I talk towards the board, can you? If I do this, can you hear me very well? You're just guessing what I'm saying. For the assignment, you need to know. So we've looked at the Hodge star operator, right? So the Hodge star operator takes a k form to a what form?
3 months.
A 3 minus k. 1 gets to 2, 2 goes to 1, 0 goes to 3, 3 goes to 0, right? The assignment, does anyone know why this was a 3? Can anyone take a guess?
It's because we were doing it in R3.
On R3, so if we're doing it on R2, it would be 2 minus k, that's all you need to know. So this is on R3. If I was to do it on R2, I would take a k form to a 2 minus k form. And let me even be nicer, I'll tell you that in the 2-dimensional case, star dx, can anyone tell me what star dx would be? Just be dy. And what would star dy be? And try again? Minus dx. Same computation goes through. You can use the theory I gave you last week. But I do want to look at the Hodge star operator on R2, and you will need that information. Everything else should be trivial. It should take you, I don't know, 20 minutes.
Do we need to use MATLAB?
No. If I can't use MATLAB, then I can't really write a question on MATLAB, and therefore you don't have to do it. Okay, so in the usual way, can someone tell me what we've been doing so far?
Curl, divergence.
I want a narrative. You're going to
theorem of
convince
calculus.
someone to join my cult that is vector calculus. How would you get them in?
Fundamental theorem of calculus.
Okay, but they're not convinced of the fundamental theorem of calculus, so how do you bring them in? What have we been doing for 2 weeks?
Differentiation theory.
We've been doing differentiation theory. That's good. You can look at the opening
And we
chapter.
started out integration theory.
And we've started on integration theory. And what did we look at when we started integration?
Parametrics.
We looked at what's it?
Parametrics.
Parametric representations of curves and so forth. Yeah. What else did we do?
Line
We did line integrals. So let me just remind everyone, so we looked at things of this type. So I take a curve C, I look at some maybe function f of x, y. Then if I'm integrating a function, I have this ds. What was the ds? Does anyone remember the word I used? The distortion in the line. This was the arc length element. Yeah, let's go with that. Let's go through an example on how to compute it, just to remind everyone. So let's look at something simple. Let's suppose I want to take C to be the line connecting maybe 0, 1 to minus 3, 2. Take F to be x, y plus 1. Just keep it nice and simple. What do we do first? We need to determine the parameterization of the line. And how do you want to do that?
T times 1 plus 1 minus T times T.
So I have alpha from 0 to 1 into R what? Into R2. Alpha T is going to be given by what?
T times 1 point plus 1 minus T times 0, isn't it?
T times the initial or final? It'll be final because it's 1 minus T times the initial. So 1 minus T 0, 1 plus T minus 3, 2. Make sense? Okay, let's simplify this. I would get 0, 1 minus T plus minus 3, 2T.
Which equals minus 3T, comma 1 plus T.
Minus 3T, we get 1 plus T. Okay, now what do we do that we've determined the parameterization? Shove it in the formula, but to do the formula has terms in it which I need to deal with. Yell it out, sorry, because death is anything.
Get the x and y coordinates of A of t into x and y of f.
Sure, I did something else before that typically though. Yeah.
You find the derivative of alpha.
Just differentiate it and then calculate the norm of it, yeah? That's what we did.
Which is just minus 3, comma 1 is the differential.
So alpha prime of t minus 3, 1. The norm of that is square root of minus 3 squared plus 1 squared. That's by Pythagoras. Minus 3 squared plus 1 squared. That's 10. Okay, yep.
A line connecting two points, so it says that alpha is the difference between the y coordinate and the x.
Of course. That's the slope of a line. Yeah? Yeah.
Sorry if this is the wrong time to bring it up, but we were assigned a surface integral in the MATLAB graded the other night, and we have.
For this week.
Yeah.
For this week, June.
Yeah.
Yes.
Yeah, the one that was on Monday had a surface integral in it. Yeah.
What I do is I send someone the question and then he puts it in. So.
Yeah. Well, I think you have to use MATLAB as well, because part of it involves computing the integral of root 1 plus x squared.
Okay, can you send me an email to make sure I deal with that?
Sure.
Not everyone. I don't need 50 emails. One is fine.
who's the class leader person?
Oh, class representative. Do we have any of them here?
Represent the class so well.
They're not really representing us.
Yeah. Okay. You're the in-person class representative. You can send me an email. Okay. We've computed the norm of the tangent vectors. Now what do we do?
We need to get x and y in terms of.
You need to.
Oh,
Everyone sounds like they didn't spend their whole weekend doing this. Surely that wasn't the case. Yeah.
Put your a and b coordinate in place of x and y. And
So this is now x, this is y, right? Excellent. Okay, good. So now f is, well, x is now minus 3t, y is 1 plus t, and then I have a plus 1.
So it's minus 3t squared, minus 3t plus 1.
Oh, you've already expanded it. No, I don't. The integration is for you guys to have fun with it. I don't do that yet. 0 to 1, and we have this thing, which I'm not going to simplify. And then we had square root of 10 dt. Okay. And that's just Riemann integration we learned in kindergarten. Okay. That makes sense, right? Yeah? What else do we do? In this direction, what do we kind of finish off with?
We did the same sort of thing, but for more general terms.
We did more general curves. We also did line integrals of vector fields. That's right. And remember, when we have a function, we calculate the norm. But when we have a vector field, we don't need to because we have what at hand. What tool do we have if we look at vector fields that we don't have if we look at functions? The dot product. Good. Okay, so let's suppose I have the vector field. What's a nice one? X sine y I hat plus e to the minus x plus y j hat. If I make the curve too complicated, then it can't be done. So that, oh well, I don't have to do the integration, you do. So let's see, be the circle. Actually, maybe I can make it even fancier. Not yet. Circle centered, it says centered, at 0, 0, radius 4. What's the parameterization?
X equals 4.
4 cos t, 4 sin t. 0 to what? 2 pi into R2 alpha of t 4 cos t 4 sin t. Yep.
Not 2 cos and 2 sin.
If you have no, it will, if it's radius, you're getting confused with the square, r squared, x squared plus y squared is r squared.
Right.
If you think about it, you take t equals 0,
Oh,
you get 4, you get, no, I was literally thinking of that as I was writing. Okay, same deal again, what do we do? Just compute the derivative. alpha prime of t
Minus 4 sine t.
minus 4 sine
Minus
t.
4 cos t.
Next, what do you do?
Take the norm.
You don't need the norm. Before you take the dot product, insert the values of x for minus 4, 4 cos t, y is 4 sine t. Same as before. Okay, so if we do that, if x is 4 cos t, what do I get? I get 4 cos t sine of 4 sine t.
This sounds like something I invented.
You'll be integrating it at the end, don't worry. I hat plus exponential 4 sine t minus 4 cos t chain x.
Why don't we need to take the norm?
Why do we need to take the norm?
Yeah.
In the function case, because there's no way to pair a vector valued function really. You want to end up with a scalar function to integrate.
Yeah.
If you left this as a vector field,
Yeah.
then
Or
you're
in
going to
this
get
case, it's like cradle vectors.
you're looking at the extent to which the vector field lies over the curve, and so the dot product produces a scalar function naturally.
So you don't need the norm.
Technically integrate vectors though, because it is summing up into the movement to the vector.
Depends what you mean by integration. You integrate forms. That's the dogma here. You integrate forms. You don't integrate vectors. Even when you understand integration of tangent vectors, what you're really doing is integrating forms. You just don't realize it. I mean, a vector is a direction with some magnitude, right? But a form, remember, is an element of this dual space. It takes in this and returns a scale. So that's what you're integrating. Let me mention it now. I have begun writing the details. If anyone wants the gory details on how to actually do this properly, it's in the appendix, which I will upload to Wattle shortly. It's not understandable. It's not designed to be understood. It's just designed to be there. Okay, so we now have our vector field in terms of the components of the parameterization. We now take the dot product with the tangent vectors. So let me do it properly. So f dot alpha prime of t, that's going to be minus 16 sine t cosine t sine 4 sine t, and then we will have plus 4 cosine t e to the 4 sine t minus 4 cosine t.
So it's equivalent to the norm sort of in a way. In that we're getting.
They should be. I encourage everyone to sit down and kind of wrestle. This all should be equivalent. There shouldn't be kind of a change in method. It should be exactly the same.
Right. Now that's something from a column.
Exactly. The norm is a dot product itself. I would like it to be much more transparent. I just haven't bothered to think about it. Okay, so we now have this. What do we do? Integrate from 0 to 2 pi.
That's something from a horror movie.
A horror movie.
Yeah.
Yeah, this one definitely puts hairs on your chest if you can integrate that thing. Is it that hard? Sine of sine. Is there a closed form expression for the integral of sine of sine? It's bounded, so it's integrable.
You can convert them into Fourier sum.
But now you have infinite series.
No, there's a certain amount of terms of Fourier sums, because sine of sine of sine of sine of sine approximates the triangle wave.
Approximate, yeah, these errors.
Yeah, I'm saying that there's a matching sum
Mhm.
which has the same error.
Oh, okay. That's interesting. Maybe I'll put that on the exam. Just some ridiculous integral that you just
How about e to the x squared?
e to the x squared. You know, that's the standard. That's the standard non-integrable one. The vague integration comes up here as well. Needless to say, that example is of no utility to anyone. E to the minus x squared is useful, but e to the x squared.
I'm doing analysis, and is that going to hit me?
When you do analysis,
Yeah.
analysis what?
One.
No. Analysis line of metric spaces.
Good.
Okay. So that's enough review.
About one and two. You were working with functions. How did you work with 0.1?
So functions are zero forms, so the procedure proceeds identically. And we did an example last week with a one form. Let me do an example right now, just to remind everyone. Since obviously they weren't using their weekends to do line integrals. Let's take omega 2x minus y dx plus 3y minus 2z dy plus y squared dz. Let alpha from 0 to 1 to R3 be the curve parameterized by minus t squared t cubed. As I give you the parameterization, don't expect that on the exam. I probably won't. I don't give it in the assignment, I think. Okay, so what do we do first? Okay, so what do I want to do? I want to integrate this, where C is the curve parameterized by alpha. What do I do? What do I do first every time? Just take the derivative. I don't like thinking, so every time it's going to be the same. So alpha prime of t. What do we get?
Minus 1, 2t,
Okay, x is now minus t, y is t squared, z is t cubed. So omega becomes 2x, so I get 2 minus t minus y t squared. Dx is now minus dt. Because what I actually do here is I let this be x, and then dx dt is minus 1. So dx is minus dt. Okay, I have 3, what's y? T squared. Minus 2, what's z? T cubed. What's dy? 2t dt. Y squared is going to be what?
2 to the 4.
T to the 4. And dz, 3t squared dt. Notice how it's already something you could integrate. Yeah?
Doesn't stop it being plain hideous.
What was that, sir?
Doesn't stop it from being plain hideous.
Oh, this is fine. This is polynomial.
Yeah, but Polynomials can be ugly too.
Polynomials can what, sorry?
They are ugly too.
You live a privileged life, my friend, if you think polynomials are ugly. You know, people spend their whole life studying polynomials. It's one of the most complicated areas of mathematics. It's known as algebraic geometry. Let me also say, if you want to be a mathematical snob, then algebraic geometry is your field. Algebraic geometry, they're the ones that, the plebs can do those calculations. We're above that. Needless to say, I'm in algebraic geometry. Okay, so let's simplify this. I get t squared, this would be minus 2t, so I would have a plus 2t dt. What would I get here? I would get 6t cubed. I would have minus 4t to the 4 dt. Here I would have 3t to the 6 dt. Sixth order polynomial. Well, is this a polynomial? What is this? Is it a function? It's all one. Good. And so, okay, I can write it like this as well if I wanted to. T squared plus 2t plus 6t cubed minus 4t to the 4 plus 3t to the 6 dt. And then the line integral over c of omega is the Riemann integral from 0 to 1 of this dt. Make sense? By the way, you'll lose marks if you leave it like that in the exam. Make sure you calculate it, okay?
In order to integrate this form, you have to change it to one, differential in one coordinate, dt. If you need to integrate the original expression of dx.
How do you integrate, hang on. What do you mean integrate the original expression?
So integrate together dx is the one instead of changing it all.
How do you integrate y? You get an x y. Is that what you mean? If I integrate this 2x minus y dx, just integrate that. Is that what you're saying? So you're saying, x squared minus xy? And how do I integrate it over the curve?
Okay, over a curve you
Yeah. This is the thing, right? This is you got this arbitrary curve that sits inside Euclidean space, and you need to pull it back to an ordinary Riemann integral on the line. That's the kind of theory. Is there a question? You should always think about why can't I just do it a simpler way, and that's what you learn. Okay. So let me try this microphone now. Okay, now we're going to talk about one of the really interesting parts of the theory. I mean, the whole subject has been very interesting so far, undoubtedly. But now we're going to start getting to some really interesting ideas. Can you hear that fine? That's okay? A bit louder or is it okay? Good? Good? Yeah. Okay. Let's, so we're now talking about path dependence, path independence of line integrals, and we're now going to start to see the meaning of the fundamental theorem of calculus. Yeah.
Sorry, just quickly, would we ever have to come up with a parameterization on examiner test?
Yes.
Okay.
Yes. Anything uncomfortable, I will get you. I think. Remember I said last week I wanted to get you guys to do dx, dy, dz in spherical coordinates. Do you remember I said this? I was going to put it on the assignment and I started doing it and I couldn't write the solution because I gave up. I did this page of calculations and it didn't come out with what I wanted it to do, so I was like,
You told me I had no spine for never doing spherical coordinates.
you need to do it. I've done it once in my life. You only need to do it once, and apparently you can only do it once.
I use polar coordinates.
You're younger than me. You've got more energy than I do.
I used polar coordinates in a 116 question, but lost nearly all my.
You won't lose marks in this course for using polar coordinates. I encourage, polar coordinates aren't coordinates, but I'll let you think about why that's the case. Okay, so. Okay, so the fundamental theorem of calculus, which we're all convinced of as being important, tells us the following. So we see what is the statement here. I want to have some level of originality, so let me. What does it mean? What does the fundamental theorem of calculus mean? Yeah. Yeah, there's a duality between integration and differentiation. So that's the perspective that you're almost certain to walk away with at the end of calculus, right? And that's not correct. It's on the right track, but it's really not. It's really missing the point, and the beauty of vector calculus, as we're going to see, is to elucidate exactly what this symbol is saying. What else does it mean? What else could it mean? I mean, it's even in the phrase antiderivative, right? That assumes this dogma. So you introduce one another. You have the same delusions. Yep.
The total change is the sum of decimal changes along the way.
Yeah. Deeper than that. Yep.
But the integral is dependent on the endpoints?
It's only dependent on the endpoints. That is a baffling statement. If you don't understand that, think about it more. If you claim you understand that, think about it more.
That's only in one dimension.
In one dimension, yeah, this is right. It's hard to see because it is one dimension. So what I'm going to do is I'm going to write this in a way that's going to foreshadow what we're going to see later. So this is a one form, right? Yeah. And we write this one form usually as one. We usually write it as OMA, but this one in particular, what is this?
df.
It's just df, it's the exterior derivative. So the integral from a to b of the exterior derivative of f, and this is what? The difference of f at the endpoints, right? But what I can do is I can think of the endpoints as the boundary of the interval. So if I take a to b, then the boundary consists of just the points a and b, right? So what I can do is I can write this as the integral over a b, by which I mean the boundary. The 2-point set consists of only 2 points of f. This is just a heuristic explanation. Do not worry about any form of rigor here. We'll get rigor in a moment. Now what I can do, what's the notation people use for the boundary of a set? Does anyone know? Did you use it in triple and five or what's it?
Symbol that means the partial derivatives.
It's the partial derivative symbol. So if I have some domain in let's say R2 or something, or Rn, boundary of omega is written like this. Okay? Like this partial derivative symbol of partial set. So for instance, if I was to take the disk, then the boundary consists of just a circle. Okay? Make sense? So this would be my omega, this would be the boundary. So let me write this further as the integral over omega. Here omega is now the interval of df. And that's now the integral over the boundary of f. Does everyone follow my nonsense discussion so far? There's no precision here, this is just heuristic. Is everyone kind of with me that this translates to an integral over the interval? So here, omega is just a to b of df, but that, by the fundamental theorem of calculus, is the integral over the boundary, by which I understand the integral over the boundary to be exactly this, of f itself. Okay? But now what does it say? It doesn't say that the integral is opposite to the derivative or dual to the derivative. It says that the derivative is dual or opposite to the boundary of a region of integration. And how do you realize this duality? It's via the integral. Okay? Who understands that? Good. This is if you go to Unitlodge, I think this statement is in the concrete. Someone has carved this into the concrete. Specifically, they've at least when I was at A&E, they had done this. This statement is in the concrete near Unitlodge, and it's this is Stokes' theorem. This is the point of the course, is to understand this statement. Okay. So don't worry, we've got 2 more weeks to understand it. It's one of the lecturers here said that you're allowed to have your favorite theorem in mathematics, but you're not allowed to have your second favorite theorem, because that one's Stokes' theorem. Okay, it's the most important theorem you're ever going to learn, and probably the most important fact you'll ever learn. Okay, you're welcome. Okay, so that's my little. If you want to hear me rant on about it a little more, it's in my video, Why You Don't Understand Green's Theory. Which I'm sure you're all subscribed to the channel and so forth already. I don't need to remind you.
This seems vaguely like you're trying to get more monetary advantage out of it.
That's why I teach the courses.
To get subscribers.
To get subscribed, how am I supposed to get the new generation on my channel?
I believe you're supposed to say, please like and subscribe.
I probably do. I probably say that at the start. And sign up to my Skillshare course and everything.
Well, I fast forward through YouTube when they say, please like, share, and subscribe.
As long as you don't rush through it on my videos, I'm not concerned what you do on other people's videos. Feel free to leave a negative comment. That seems to be the thing people do.
What's the mark penalty for liking a negative comment?
What was that, sorry?
What's the mark penalty for liking a negative comment?
The mark penalty for leaving a negative comment.
How many marks do you lose for leaving a negative comment?
Well, you'll find out. Especially when I find out if you use the fake accounts to just leave negative comments. Okay, so this is the theorem that will be extremely important for today. It's called the fundamental theorem of line integrals, and it's exactly this statement here. It says that if I take the integral, the line integral of a gradient field, so the vector field is nabla f, then it's given by the values of the potential at the endpoints. Notice that that is exactly this statement, because Because remember that if f is nabla f, then omega f is what? Df. Now I can write this as, just to illustrate how it is this statement here, I can write C as omega df, and now I would take up there the value of f at the endpoints, which would be exactly this. So here is f and omega are replacing one another. Yeah.
Just to clarify, what is the notation mean on the second line on the right-hand side as well?
Second line, right-hand side.
Yeah, that.
This means the integral over the boundary, the 2-point set. So it's not the whole interval, it's just the endpoints. And by definition, it is this. This is a heuristic argument, just to get the So this is an illustration of the statement here. Does everyone agree with that? Okay, so it says that if I have a gradient field, then the value of the line integral is independent of the path I choose. So for instance, I take a path like this. So I take, here's my point A, here's my point B. I take this, and I take that. Two distinct paths. Doesn't matter. The value of the line integral is still the same. Does everyone agree that that is highly non-trivial? It's not even, it is not trivial. This is a very important statement. This is, I still don't understand. Good thing I'm teaching it. Okay, it's 9:47. I got a couple more minutes. Okay, so I'm going to say that a line integral is path independent if this is true. Okay? If it doesn't matter on which path you take, and I will say that a vector field has the path independence property if the following is true. Okay, so what we're seeing is that gradient fields have the path independence property. So gradient fields imply path independence. Okay? Yep.
Is this one for scalar field?
Fundamental theorem of calculus would apply in that case. It's the standard version. Okay. So if this is true, if it's independent of path, what can I say about if I go around and come back? It should be 0. Because I would go this way, and then when I go the other way around, the line integral isn't the same, right? What is it? If I go from B to A, it's the minus. So when I add them together, let me do that explicitly. So let's call this C1, C2, and yeah, so the line integral over C1 and C2 of, or how do I want to write this actually? Take a loop. Line integral over the loop. By loop I mean this, of f. That's the line integral over C1 plus the line integral over C2. No, it's minus C2. But now, because they're equal by path independence, it has to vanish. So a gradient field, if we look at the line integral over any closed loop, and let me suppose that it's sufficiently regular, then it will bound like that. Okay? Does anyone have any questions? Yep.
Is the statement that the integral of f is path independent the same as f is a gradient field?
They are equivalent if the thing is simply connected, so that's what we're about to get to. Yeah. Yeah, part of the course, so the main part is to tell you what the fundamental theorem of calculus means. The other part is to essentially tell you what cohomology is without teaching you cohomology. And what is really going to be key, at least for assessment, is understand implications. So we know this is true. Is the converse true? Irrotational vector fields on simply connected domains, you know, path independent and so on. Okay? And don't worry, I'm going to start, like I'll probably have a whole lecture just on reviewing implications. Okay? So here's the statement there. Just formalities. The first curve is not a closed curve. Doesn't, the end point and start point are not the same. The second one is a closed curve. Okay, let's, by the way, if you don't know what path connected open subsets of Rn are, do not worry. Is that a question?
Yeah, this might be a really stupid question, but we did draws over circles just earlier.
Mm-hmm.
Is that
That's a closed curve.
okay?
But the thing was not zero, right? So it mustn't be a gradient field. Yep. Good. That's a good question. Yep.
Can you scroll upwards so you can still get the definition of the closed curve? Or is that not possible?
That's, well, always good to have definition. I don't think I'm allowed to assess you on defining this. If it was Math 2405, which used to exist at 100%, I would be asking you to define everything. But 205, I'm not allowed to write a question saying define what a gradient field is. But if you don't know what that is, you're going to have a tough time. Okay, almost 9:55. Does anyone have any questions before we take a break?
Practice quizzes on Wattle.
Say it again, sorry?
There's these practice quizzes on Wattle, right?
Yes.
Now, I don't know if you saw my forum post about this.
I try not to look at the forum posts.
Why?
Because then I have to respond to them. And then I'm getting questions about all types of things which I explained 300 times.
But
Let me reiterate as well, because this is something that I mean, there was a whole post made about like the degree to which this is not understood is striking.
but
If you want to do well in this course, read this book. That's it. Okay? Does everyone agree that I'm following this book extremely tightly? If you read the book, you will get 100% of the course, assuming you understand it.
no, this new 2022 new practice quiz 1 is given 0.99% of our final mark as weighting.
But it's not due anytime soon, right?
No, but it shouldn't even exist.
Well, I don't want to worry about that. These practice quizzes, I think the way we designed or discussed them were you get additional practice problems to prepare for the final exam.
Exactly, it shouldn't be worth.
So if you do them, you get the benefit of learning, and I think you get like 0.99% of a mark. Just do it.
But do you have to get them right?
I think you get infinite attempts.
Oh.
So, yes. But it may take you an infinite amount of time if you don't study material.
The integral from infinity to minus infinity would be
I'm not going to worry about it now. Okay. Does anyone else have any questions? I mean, it's 9:55. You can, yeah.
Is the recordings on Echo has audio only, and
Yes.
is it possible to record this PDF and upload it?
I wish I could. I've tried to do it on this, and it just doesn't do it. I don't know how to do it, but the board is okay,
Yeah.
and I do follow it just linearly. In the sense, you really don't, in my opinion, you don't even have to show up to the lectures. The book is written so thoroughly that you would never have to come.
You have a very high opinion of the world.
Does anyone not like it?
Could use a few more jokes.
Jokes are frowned upon in algebraic geometry, so we don't do that.
I don't like geometry. What area of maths?
You don't like geometry, then the door is right here.
What area of maths is right for me?
Integration theory.